Okay, time to continue with polynomials. And we are now going to be combining this idea of polynomials, which is rather concrete and you've known for ages, with something rather new that we talked about just recently, the ring structure. So ring is an algebraic structure where you have addition, subtraction, multiplication, a 0 and a 1, with suitable algebraic laws, but we'll not focus too much on the laws here. And polynomials, for polynomials we can define all of those operations as well. And here is about one of the cases for how to define that. And we will use it as an example of where we transport structural operations sort of backwards through homomorphism. So we know we have defined addition, subtraction, multiplication, 0 and 1 on functions. So we have this additive and add group and multiplicative instances for functions. And that is the result of eval. So we know how to do those operations there. Question is, can we move those operations backwards, up the chain sort of, to the syntax for polynomials, to define corresponding operations on just lists of coefficients. So basically we want to make this eval a ring homomorphism. We wanted to preserve the operations from the syntax level to the semantics level. Okay, so basically the question is, for one of the operators then, does there exist an add such that eval takes this add to function addition? I'm writing function addition here as a plus with a ring, as we did in a few lectures back as well, just to keep track of the types. And we know from the way that homomorphisms are defined, this age2 predicate, that eval will take a list of coefficients to a function. So the whole add must work purely in the A world, the list of coefficients world. So it should take two lists of coefficients, in return a third list of coefficients. And I'm sure you can roughly guess what this function should be, but let's try to reason about it from the mathematical point of view here. So we have a few cases, and we'll start with the simplest ones. So if we are trying to add an empty list to any list, say x's, then what should we return? Well, if we look over on the left, we see that the empty list is representing a constant function returning always 0. So if we, on the other hand of side of eval, we will get a 0, basically a 0 out, the 0 in the function type. So this means that we will have to return something here which will evaluate to the same thing as this. Well, and we have something that will definitely evaluate to the same thing, and that's the same list. So basically, if one of the lists of coefficients ends, then we continue with the other list. So then let's add a symmetric case. So if we want to add the opposite, the empty list, on the second component, then add is commutative, so we should get exactly the same result. So together, these two cases will cover all the cases where one of the lists is, at least one of the lists is empty. So now, after covering these two cases, we know for the last case that both lists are non-empty. So here we could show that pattern matching wise by saying add of x cons x's and y cons y's equal. So here we have a little more information, and we will get back to the exact definition later. And here I'll just call this sort of the core case. That's the core of the definition. But we should note that there is quite a bit of information in the two first as well. So for example, if one polynomial is just the empty list, then we return the other one. But also, when we recursively go to two polynomials, if one ends earlier than the other, then we will just continue with the other polynomial. So that means that we will sort of retain the higher coefficients. We will basically treat all coefficients in this empty list as zeros. So we add 0 to all coefficients in the other list, and that gives us this. Okay, so this is on the way to defining this add function. Let's, and this was the cases I already shown. Let's try then to prove that this add is satisfying the homomorphism condition. So, that eval is a homomorphism from add to function plus. And this is stated up here, eval takes add to function plus, and we've expanded it, saying that for all pairs of lists AS and BS, if we first add them syntactically and then evaluate, which gives the same result as if we first evaluate both to functions and then add them up. And notice here that the equality here is not really implementable in Haskell, it's an equality on functions. But mathematically speaking, this is quite okay. So I will practice here a proof by structural induction, and it's a simultaneous induction on both lists. So we have this predicate P that we want to prove, which is exactly this copied down. So P of AS and BS is the homomorphism condition. And then we have 4 possible cases. We have when both are empty lists, and then when one or the other is an empty list, and then finally the core case, where we assume an induction hypothesis, IH, that the predicate holds for these two, and then for all A, B, AS, and BS where this holds, it should also hold for the extended lists. And basically that will build up, starting from these sort of base cases, we will build up all pairs of lists. And if we can prove these 4 cases, then we can get the conclusion here that for all AS and BS, we got the property P, which is what we're seeking. So notice that it might seem circular to assume the property we're trying to prove in the middle here. But when we assume it, we prove something stronger. We prove something for a longer list. And that's the power of induction, that it will take us one step up at a time, and then we can make the list as long as we like. Okay, so now let's try to do this proof. So we want to prove P for the extended lists, assuming the induction hypothesis. And I'm not sure why suddenly this slide has become sort of low resolution, but yeah, okay. I've written here already, because I sort of tried to type it out to make sure it fits on the screen, the arguments, the steps, because here, this is not really a practice in getting what the definition should be. It's more a practice in doing equational reasoning as a proof method. So I will take steps here, and in each step I will motivate which definition or lemma or induction hypothesis and so on I'm using. Okay, so I start with the expression I want to work with, in parentheses, applied to x. So it's slightly easier in this calculation to do it applied to an unknown arbitrary x here. So that's what I will do. So this is a real number. The individual eval results are functions. Adding them up becomes a function, and apply it to a particular arbitrary x will then make it just a real number. Okay, anyway, so the definition of this plus says that if we have two functions, we add them up and we apply them to an x. That's the same as applying each function to the same x and using normal addition instead. So that's the next stage. So we can call eval on a cons as on x, and then normal real number addition to eval b cons bs on x. Okay, so if we have got to this place, we can then see, okay, what could we do to get further? I will just clean up this AS a bit. Well, we've got an eval on a pattern, and we have a case for that. We have a definition of eval just up here. So we can just apply it and get the right-hand side. So in two cases, both for AAS and BBS. So this is then A plus, and I'll put an extra parenthesis to make sure we see where we are. A plus eval, no, sorry, that was too early. A plus x times eval of AS applied to x, end parentheses. And if I want to copy this, what I had above, I should try to make this. So I'm just using this right-hand side down here. And not surprising, I'll just keep the plus in the middle and have b plus x times eval bs x on the right. So that's application of the same rule, but now I have b instead of a and bs instead of as. Okay, so I was saying this was for an arbitrary ring, so a data structure where we have addition, multiplication, and so on, and there are certain axioms that should hold. For example, addition here is associative and commutative, so we can move around the terms. So I'll collect the sort of non-x terms, the constant terms, on the left. So in the next stage, I will say, okay, this is a plus b plus. And then if we notice what's left, we can see that there are two terms, both have x multiplied in front. So I use the distributive law and say, okay, this is also then x times, and then a parenthesis, and these two terms. So one is eval as x, and the other is eval bs x. Okay, now I will use the definition of the function plus again. So I notice we have a real number plus and two functions applied to the same argument. And that pattern is exactly the definition of plus with a circle. So here a plus b is not changed, x times is not changed, but in here I've now got eval as plus with a circle, eval bs. So adding up the two functions and applying the result to x. So notice the space here between this function and x is function application, it's not multiplication. So I'm trying to write the little dot for multiplication here to avoid confusion. Similarly, this is not eval times as, but it's eval function applied to as, and so on. Okay, now the reason I wanted to get here was that now I have something in the shape of the induction hypothesis. Remember, I wanted to prove something for the longer list, and now I got an expression which is exactly what I had with the shorter list here. So I'll just replace that equality. So it's still a plus b plus x times. But now, instead of this eval plus, I'm using the eval. One call to eval instead of two calls to eval. So this is eval of add as bs. And then applied to x. Okay, and now I recognize the pattern here, that I have some constant x times a call to eval applied to x. And that's exactly this rule again, but backwards. So here, the a is a plus b, the as is add as bs, but the x is just x. Okay, this means that I can sort of backwards translate this to one call of eval, and then what list? Well, the list is now a plus b as the first element, followed by add as bs as the second element, or as the rest of the elements. That's a list. And then the whole thing is still applied to x. So notice how I'm using this side here. Okay, and what I wanted to prove was that eval should just have add in here. Add not for as and bs, but add for a cons as and b cons bs. So let's first just write down what I want it to be. So I want it to be eval of add of a cons as and b cons bs applied to x. And now I've marked in green here that this is not by argument for something that already exists, but here, as we haven't defined add yet, we're looking for, is there an add? Does there exist an add? So basically this is saying that, well, if we define add in such a way that when it takes two non-empty lists, it should add up the first components, put it in the front, and continue recursively with the rest of the lists. So if we define add, which was the core left in the definition of add, if we define it in this way, then the proof is done. And we're free to define it, and we were just trying to see, does there exist any add? So let's take this definition. So remember, we already had add defined for the other cases. So I've summed them up here. Actually, I also specified separately this one, but that was a special case of the others. And the only new thing, the core case here, was one we actually arrived at by trying to prove the induction step and noticing that if we only could get add of these two arguments to be equal to this, then the whole proof would be getting through. So let's have that as a definition. Okay, now looking at what we've achieved, we have proved that eval is a homomorphism from add to function addition, if this definition of add is used. And the actual definition, you can see, it goes lockstep through the two lists, sums them up components-wise, and then continues. So for example, if the lists have the same length, they would just continue summing the components pairwise, so the 0th component to the 0th, the first component to the first, and so on, until it gets down to this two empty lists, which is just the empty list at the end. But, and that, well, I should say, that one we recognize as zip width. So I should say this is a bit of a danger zone. This is almost the function in the Haskell prelude called zip width plus, but it's not equal. So the reason I'm saying it's almost is that if we leave out these two cases, or rather, if we, instead of these two cases, would have the empty list here on the right-hand side. So let's put that in red as wrong, sort of. If we would have empty list there and empty list here, then we would get zip width. And what does that mean? It means that as soon as one of the polynomials ends, the other polynomial will be thrown away and the 0 returned. So for example, with zip width plus as the definition, we would end up that 0 plus xs is 0, which is definitely not what we want. So I call this add function, or a generalization of it actually, zip with longer. So as you see, it does zip with. It zips the two lists together, pointwise using addition. But then when one of the lists is longer, it keeps the longer list. So the sort of the green, the real function, so it's almost zip with, but it's not. But the real function here is also called zip with longer of plus. Okay, so now when we have this, it means we can make an instance of additive for lists of real numbers, where addition is our add and 0 is the empty list. And it will behave as addition of polynomial syntax tree, well, syntax list, coefficient lists. Okay, so this was all for this part.